Good morning, students. We have already discussed our radius whenever particle enters into magnetic field, and that is equal to mv over qb, radius of the charged particle inside magnetic field. And we also discussed cyclotron frequency, that is equal to qb over m. And this cyclotron frequency only depends upon charge to mass ratio. Okay, and it does not depend on the velocity of the particle. So cyclotron frequency does not depend on velocity and also on the radius. It also does not depend on the radius, velocity and radius of the charged particle. As long as b remains constant, so for a given particle the angular frequency if remains constant. For example, if we have an electron, so electrons, for example, the electron that moves the path of small radius will have low speed, and the electron that move in large r, so it is speed will be faster. It will be faster if we have given same magnetic field. So if magnetic field is same, so the electron that has large radius, whose radius is large, for example this is E1 and this is E2, electron 1 and electron 2. So the electron whose radius is this r, and the electron whose radius is this. So the, for example, this is r1, this is r2. The radius r2 is greater than r1. So the electron in this radius will move faster. In this radius, electron will move slow. As a result, the cyclotron frequency will remain constant. Will be same. So cyclotron frequency is independent of r and v. And now we are going to discuss the first particle accelerator, cyclotron. So you know that particle accelerator is a device it is a particle accelerator that accelerates the particle, that is used to accelerate charged particle. So the cyclotron, there is first particle accelerator is made up of two D's. For example, if we have two D's, that is two conducting hollow D's made up of metal, and their straight sides face to face. So there is a cyclotron. So cyclotron is made up of two D's like this, metallic hollow D's. D1, for example, this is D2. So in cyclotron, we accelerate the particles, and this is connected with a variable potential or oscillator. So charge particle, there is potential, variable potential, and there is magnetic field. So for example, if we keep here magnetic field that is coming out of the page, for example, magnetic field is coming out of the page. So magnetic field is coming out of the page, and first we give it this D is a higher potential, we keep it at higher potential, means it is positive, and this is negative, and particles are created at the center. For example, here a proton is created, for example a charged particle Q is there. So if this is charged particle is produced at this location, at the center of the gap between these D's, this is a gap between the D's. So when this is positive plate and this is negative plate, the electric field is in this direction. So E field is in this direction. So what will happen? That first particle will accelerate because it is in electric field. It will gain acceleration because electric field can accelerate the particle. So electric field will exert the force on this charged particle, and this will accelerate, and as it will enter into the D, there will be no electric field because inside the conductor electric field is 0. So inside this conductor E is 0. So this, because this is metallic hollow D, so as it enters into the D, there will be electric field, there will be magnetic field. So magnetic field, because particle has velocity, so there will be acceleration, the magnetic field will bend the direction of the particle. So this is the velocity direction, and the magnetic field is coming out, so force will be outward. So the particle will bend its path. So as it comes at this location, now particle velocity direction is in this direction. So now we will vary the potential difference. Now this plate will become positive and this plate will become negative. First this plate was positive and this was negative. Now this, due to variable potential, this will become positive and this will negative. So now electric field's direction will change. So for example, if we apply here 10 kilovolt potential difference, so the as electron enters into the electric field, it will gain 10 keV kinetic energy. So now electron will have more kinetic energy, and it is radius as it is radius was for example R1. Now its radius will become more larger. Again, when electron will reach this gap, again it is radius will become, again it will gain the kinetic energy, and its radius will become large. So it will spiral like this. So the particle radius will become bigger and bigger, and the velocity with which it will leave this cyclotron will be, we know that mv is equal to qbr. So velocity will be qbr over m. So that will the velocity with which it will leave the cyclotron. And the kinetic energy of this particle will be, we know that kinetic energy is equal to 1 over 2 mv square. So that will be equal to 1 over 2 m q square b square r square over m square. One m is cancelled in m, and the remaining expression will be this expression for the kinetic energy of the particle, charged particle. So now we will consider that magnetic force do not work. So if we have a charged particle q, it moves a distance dl. So if it moves a displacement dl, that dl is given by the velocity of the particle and a tt time. And if we want to find what work it will do, small work dw, that will be d means dl here, small length, dw will be equal to f dot dl. So f is here magnetic because it is magnetic work. So f magnetic, we know that q vb qvb cross b, and if we here dot with dl is equal to v dt. So if you cross with the same vector, this is same vector, this is same vector, if you cross both vector, so the resulting vector is 0, null vector. So vb cross v will be equal to 0. So T magnetic work is equal to 0. So magnetic field can not do work. It cannot speed up, or down a particle. It can only change the direction. So it cannot change also kinetic energy of the particle. It can only change the direction of the particle because velocity force is always perpendicular to the velocity.